Welcome to my friends. So today I am going to give you an idea about a field oriented control which is implemented using high speed PLC and microcontroller. That means PLC and microcontrollers, they are in the microcontroller is interfaced with a PLC. So microcontroller, here the microcontroller job is only to generate the PWM pulse for the inverter. This I have tested today in my lab once again, because this earlier I have used very high speed PLC, and today I have used very off the shelf low cost PLC also. So I have tested it and it is successfully generating the required pulses. So that just for one experimental purpose. Earlier I used Rockwell PLC. So today I have used a very low cost simple PLC to generate the modulating signal for the PWM, and it is successfully generating the desired pulses. So that scheme just I am going to share. I am going to share it with you. So first come to the code. So here I'll not go in depth of this code, because this I wrote in which one? Arduino IDE. So here simply just I want to show that the ADC is reading. So here all the details, means this register settings, okay, and this ADC settings, all these things I'm not going to discuss because it is slightly, because here I have used the prescaler, okay, and these bits till the conversion I am not allowing to do other activities. So this code can be modified, and I am using timer overflow interrupt. Okay, so once the timer this overflow interrupt is occurred, then the program counter, it will be redirected to this service routine, and it will check the value, this X and Y, and based on that this output compare register will generate the PWM of a desired duty cycle. So here I am reading this value, I am reading from the ADC. So ADC is reading the value, and it is the same value is going to the output compare register to generate the desired duty cycle. So let us see the simulation first, so that I'll slightly bada karega. So let it be like this. So here I am showing you two pulses, means OCR1A and OCR1B. So this is the modulating signal. So this modulating signal is this is 5 volt pulse, peak to peak it is 5 volt and 50 hertz. So if that signal 50 hertz or 60 hertz, whatever may be, it will be coming as the modulating signal. So based on that this PWM will be generated. So if I simulate it, so let us simulate. So here I have used simple one low pass filter. So here cutoff frequency is FC is equal to 1 by 2 pi f RC. So based on that I have selected, and here cutoff is 50. So if put the cutoff frequency as 50, then if I select the resistance as 10K, then accordingly this will come as C. as per the formula. So simply it's a low pass filter of cutoff frequency 50 Hz. Okay, so now you see, I'll run it. This pink color signal, basically this pink color signal is the input signal to ADC, and this signal, it is going to the ADC is reading this pink color signal, and that value is going to output compare register, and it is generating this kind of pulse. This yellow color is the final output. Okay, unfiltered, if we see, I'll connect one more channel here. This is the unfiltered signal. You see, this is the PWM pulse. This green color is the PWM pulse, which will be going to the inverter. Okay, so here there will be a module. We have to make a board, that this board will be receiving the in case of 3-phase inverter, this module will be receiving the modulating signal from the PLC after processing all these things. Then this PWM complementary PWM pulse for 3-phase, it will be given to the inverter stack, and it will rotate the motor. This is the idea. Now I am going to explain the scheme. So let us take a pen. So this is the PLC. So here I have used a TSX P572634M CPU. Okay, and here basically what is to be done. So this is the inverter module. This one is the inverter module. This inverter module is connected to the motor 3-phase. This inverter is 3-phase 2-level inverter, and here I am sensing the RPM. Okay, this is the induction motor, and here I am sensing the current. Okay, so now in this PLC, what are the cards are needed? When we are reading the incremental encoder pulse, so we need to have one high speed counter card, HSC card. Then we will be using, we will be sensing the current. So we need analog input card, and in between some sensors are there. All these things I am not detailing, just I am giving you the overall view. And this PLC is connected with this interface with this GUI. Okay, this is XBTGT series, even though it is very old, this series. So here, so this is the modulating signal, A phase, B phase and C phase. This will be coming from analog output card. And this is the PWM card. That means it will, this VA, VB, VC, it will be reading by the ADC, and that ADC value, it will be going to the output compare register, and this will generate 2 complementary pulse for 6 switches. So this is for A phase, this for B phase, this for C phase. Okay, and inside this PLC, whatever the things it will be done, it will be there. The direct axis loop, so, and the quadrature axis. So direct axis there is a single PI regulator, so that PI, KP, PI, all these things, it will be set through this GUI. Okay, so in quadrature loop there will be a outer speed loop and then the inner torque loop. So this will generate VD and VQ. This will go to one DQ to ABC transformation. Okay, so this will go to DQ to ABC transformation. This it will generate the modulating signal VA, VB, VC. This is going to going here, and here one thing it will be there, theta estimation, because here we are aligning, in this concept we are aligning the instantaneous rotor flux with the direct axis of the synchronous rotating reference frame. So main thing is this PLC is used to generate that modulating signal for the three phases, and this hardware will be taking that, will be reading that three-phase modulating signal by the ADC, and this ADC value it will be updated in every overflow, timer overflow, to generate the pulses. So this is the basic scheme, that because in the microcontroller we can do it, all the things we can do it in the microcontroller, but for industrial application, these products, this is Schneider products, and all these things are proven for industrial application. So when we are going to design something, always it is better to use the off-the-shelf component. So this is a conception, and this we will implement. This is a proposal. This is my one proposal with one university to design this system for medium voltage application. So for microcontroller there will be a limitation of output compare timer limitations. There will be 7 timers available in the controller, but once the multi-level, we are going for multi-level, there the timer requirement is more. So in that case we can use the DSP or microcontroller core or DSP core with FPGA as peripheral. So that time we can generate more output. Okay, so this is a concept that using PLC very easily we can implement the vector control of induction machine. So this only I just wanted to share with you. So hope this conception will be useful to you, and if anybody want to implement it, you can contact me through my contact details given in the description of the video. I will be then explaining you from the scratch how to do it. Thank you so much. Thanks for your assistance. Thanks for your patience.